This is the screencast for Wednesday, September 11th. Classes were canceled in person due to the Hurricane Francine. So we'll go ahead and begin Module 2, which is structural elucidation using spectroscopy. So in Module 1, just to recap, we learned about communicating structure in organic chemistry using our abbreviated periodic table, CNOF, where we were looking at these neutral bonding patterns. So carbon forms 4 bonds, nitrogen 3, oxygen 2, halogens 1. And keep in mind that these can be different types of bonding patterns. We learned about hybridization, which was a way of describing how the bonds we see in molecules differ from electron configurations and atomic orbitals. So the atomic orbitals hybridize to form these sigma, for like 4 sigma bonding carbons, so like sp3, sp2, and sp. And so again, those are combinations of sigma bonds. So sigma, that's 4 sigma, no pi bonds. sp2, 3 sigma bonds, 1 pi bond. sp, 2 sigma, 2 pi. And so just keep in mind that the heteroatoms N and O can also be hybridized based on the functional groups they're present in. And so let's now dive into, now that we can interpret structure, how do we know that a substance is actually that structure? And so that's the essence of spectroscopy. So spectroscopy is the interaction of light with matter. And remember that from Gen Chem or Physics 1, that light can be both a wave or a particle. So this is typically, called the duality of light. Light has, it's a spectrum, so it exists on the electromagnetic spectrum. There are many different wavelengths of light, from low energy radio waves to high energy X-rays and gamma waves. So we're going to look at a couple of these different types of light and how they interact with molecules and the information we can gather from them. The first technique that we're going to start with is called mass spectrometry. And notice the difference here. Metry is actually measurement. So mass spectrometry doesn't actually deal with light, but it does tell us information about the molecules we're studying. Infrared spectroscopy, commonly just called IR. So infra means before, so before red. So it's a low energy light that we're dealing with, and what it's going to help us understand are what functional groups are present in the molecule. Really specific, we'll look at regions of the data, but things like OH bonds, NH bonds, and carbonyls are going to be the things we're looking for primarily, because every organic molecule is going to have a carbon-carbon bond, carbon-H bonds. Those aren't too diagnostic in IR. The last one is called nuclear magnetic resonance spectroscopy, or NMR. And so this deals with radio waves and how they affect the spin of the nucleus. And from that, we're basically able to determine the unique H and unique C's in the molecule. So that was the point of doing that exercise in Module 1 of determining uniqueness of H and C sets, because that's going to help you interpret the data when you actually see it. And the reason we're doing this chapter now on spectroscopy in semester 1 is that as we run reactions, reactions can produce more than one product, and we need to know how to differentiate those products to confirm what was actually formed. So this is a slide I call learning to learn. And again, organic chemistry is very abstract. And you have to have this constant feedback cycle of how you're learning the material. And probably the most formal thing on here is called metacognition. And that is the ability to think about one's own thinking. Really, are you aware of how you're processing your thought patterns? And it's, for lack of a better word, it's sort of an internal feedback loop. Are you considering all the data you're presented? Is it self-consistent? If things aren't consistent, what doesn't make sense? And then how can you make it fit better? A heuristic, perfect is the enemy of good enough. Really, you have to start somewhere. And, you want to get to the right answer, but, that's a journey to get to the right answer. So if you, do your first iteration and you're not correct, but you've learned some things, you go through the second iteration and you revise. What did that first sort of initial analysis tell you? Sutton's law. I like this because it gets to the intent. A reporter, Mitch Onstad, asked Willie Sutton, a bank robber, "Why do you rob banks?" And Sutton's response was, "Because that's where the money is." And so that's the most obvious thing, right? There's money, I'm going to go get it. But Sutton was probably getting at something deeper, like, what is the purpose? Why do you need this money? Occam's razor in the medical field, otherwise known as Woodward's aphorism. So might be a new word for you. When you hear hoofbeats, think horses, not zebras. So what do you know? And don't get too exotic with your thought patterns. So what are the things you've learned? Now put them into practice. And then finally, a quote by Ernest Hemingway that I like. All the symbolism is shit. He was saying the shark is a shark. So what is the data telling you? Just pull it out of there, get the simplest facts first, and then start building a case. But again, all of this takes time and effort to develop the algorithms of problem solving. So one of the first problems we'll consider in relation to mass spectrometry, abbreviated MS. Again, what this is telling us is the molecular weight. States, given the mass, molecular weight of 86, how do we determine the molecular formula for an alkane? So let's just write down what we're given. So mass is equal to 86 grams per mole. And we need to determine a molecular formula for an alkane. And we've stated pretty much in every lecture, an alkane has a molecular formula of CnH2n plus 2. So there's no heteroatoms we have to worry about. Furthermore, we know from the periodic table that carbon has an atomic mass unit of 12, and H is 1. So what we're basically trying to solve here for N in that equation, and something that fits into the H2N plus 2. So to kick us off, what we want to do is, what's the maximum number of carbons that can be in there? Like the maximum. So it's not the answer right now. This is our first step towards finding the answer. So we can just take 86 and divide that by 12. And we'll get a number 7.16 repeating, and we're just going to call that 7. And then we're going to say n equals 7. So if n equals 7, if we take 12 times 7, what do we get? 70 plus 2 times 7 is 14. So we get 84. So 84 of that mass belongs to carbon. And then we can say 86 minus 84 equals 2. So that would get us 2 hydrogens. And so the molecular formula would be C7H2. And just by looking at that, we can say, okay, that does not obey 2n plus 2. So to a first approximation, we know that it can't be 7, it can't be 8, because that's going to blow past 86. So we're going to go down to 6. So if we say n equals 6 carbons, what's the mass contribution then of carbon to that 86? So 12 times 6, what do we get? 60 plus 12, 72. And we take 86, that's the total. So remember, what that's telling you is CnH2n plus 2. We're going to subtract 72. That's the carbon contribution. And then from that, we get 14. That's the H contribution. So C6H14. And now, does that make sense for an alkane? So when n equals 6, 2 times 6 plus 2, that's 12 plus 2, that equals 14. So this makes sense. So we get an alkane formula. But we've sort of already confirmed that 6 is most likely the right answer, but let's sort of bracket the 7 on the high end, and let's just go down to 5 on the low end to really confirm that 6 is the right answer. So if n equals 5, 12 times 5, that's what, 50 plus, okay, so 60. And again, that's going to be the carbon contribution to the molecular formula. So 86 minus 60, that gets us 26 hydrogens. So C5H26. And we recognize that for n equals 5, 2 times 5 plus 2, that's 12 hydrogens. So 26 hydrogens for 5 carbons is no good. So this is basically confirming our molecular formula that for a mass of 86, it has to be C6H14. And so this slide recaps that thinking. Again, alkane means only C and H are present. There's no degrees of unsaturation. So again, it has to be CnH2n plus 2, what we come up with. We took 86, divide by 12. Again, this is total CnH2n plus 2. 12 is the carbon contribution. We do that, we get 7. We figure out what is the contribution of 12 times 7 to that 86. We ended up with 84. That only leaves us 2 hydrogens. And so that really cannot make sense. Again, for n equals 7, 2 times 7 plus 2 gets us 16. So that's basically telling you that there's already a deficiency of hydrogens because we came up with C7H2, and an alkane should have C7H16. So already there's a lot of degrees of unsaturation in here, and we figured that out by subtracting this. So the theory minus what we figured out, or the given, we get H14. We divide by H2, that gets us 7 degrees of unsaturation. That's quite a bit. So it does not really make sense for n to equal 7. And this is just a structure that I came up with 7 carbons, 2 hydrogens that could have 4 degrees of unsaturation. And you'll notice that looks pretty bad. You know, you have an sp hybridized carbon. We know that those carbons have bond angles of 180 degrees. We're showing a ring. So naturally that bond angle is going to be quite constrained, as you see in the drawing. So there's going to be quite a bit of strain in this molecule, and that's bad. We'll talk about strain in Module 3. But ultimately it doesn't obey what we're given in the question. It has to be an alkane. So again, that's the metacognition part of this. We're circling back and saying, okay, it can't be this because of this evidence. We then knocked it down 1. So we figured out 7. We went down to 6. We ultimately went down to 5. And that's the logic you want to have is, you know, I just call this bracketing. So that your claim of what is the right answer is, you're getting the right answer, but you're also showing proof of the wrong answers. So we went down to 6 carbons. That gave us a mass contribution of 72 for the carbon count. So the total minus the carbon, that gets us the remaining hydrogens. We know that hydrogen has atomic mass unit of 1, so that's 14 hydrogens. That obeys the alkene general formula. There's no degrees of unsaturation, so we're looking good. And then we said, are we done? Yes, but no, because we still wanted to do that n equals 5. Just to really paint the picture of us being correct and using all the evidence we can to 100% or unambiguously say that it is C6H14. And so if you start thinking of those terms as like your solution is a claim, how confident in your claim are you? Yes, you can put an answer down, but do you have the evidence or data to back it up? So we went through 5 carbons. That gave the carbon contribution of 60. We ended up with 26 hydrogens. That's like way too many. And so no, that's not a reasonable molecular formula. And then in this table, we're just highlighting our attempts where we started with n equals 7. We found there were 2 hydrogens, way too many degrees of unsaturation. It doesn't obey the alkane formula. See, attempt 2 with n equals 6, that gave us 14 hydrogens. And so that's right on the money. And then 5 is unreasonable again because there's way too many hydrogens. So this type of problem, you're given a mass and you're asked to figure out, carbon count, hydrogen count, and then does it make sense in terms of a molecular formula? But there's an issue about what if you have heteroatoms? Nitrogen, oxygen, halogens. How do we use mass spec to determine if they're there, or what diagnostic things can mass spec tell us if they're not there? So we're going to start off with an example called testosterone. And testosterone is a steroid, and a steroid is a hormone. And that's a molecule that triggers a biochemical process to start, continue, or stop. So these are things that exist in our bodies naturally, and they're basically saying, okay, at this age, we're going to ramp up production of this hormone, and it's going to trigger this process to happen. And so let's walk through sort of the exercise we just did. But now we're given the structure of testosterone. It's right there. We're going to go through exercises we did in Module 1. But then we're going to pose the question later on, if we didn't know the structure of testosterone, but we did have its molecular weight, could we convert the molecular weight into a molecular formula? And then using that molecular formula, could we then propose the structure of testosterone? And so that's going to open up the sort of floodgates for infrared spectroscopy as well as NMR spectroscopy. So what is the molecular formula? And, you just sort of go through the counting carbons, counting hydrogens. Probably the easiest thing to count first is the oxygens. There's 2 of them. And so automatically we can eliminate choice A because that says 3. All the other ones have the oxygens correct at 2. There's one sort of tell in B, C, and D, where basically C is going to be the right answer because there's an even number of hydrogens. You'll see that B and D, they have odd numbers of hydrogens. And there's like certain things you'll notice about the presence of heteroatoms when you can have an odd count of hydrogens. But C is the correct answer, but let's just walk through and we'll count. And when you're counting, you can do this many different ways. I'll just draw some dots. But I want to follow the carbon backbone in a sort of specific way. I don't want to hop back and forth from left to right. I'm just going to walk the backbone. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there's 19 carbons. So right there we can eliminate B. And let's count the hydrogens to confirm. So what I'll do in blue, I'll just write the number of hydrogens by each carbon. So there's 2, 2, 0, 1, 0, 2, 2, 1, 1, 0, 3, 2, 2, 0, 1, 1, 2, 2, 1, and 3. So if we add those, we get 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So that's going to eliminate D, and we end up with CH28. Again, I'll talk more about, looking at a molecular formula and the hydrogen count as sort of a trick maybe where you can spot the right answer without sort of going through that exercise. So we have C19H28O2. So C19H28O2. And we want to calculate the molecular weight. So again, module 1 type exercises C, H, O. So how many? 19, 28, 2. Atomic mass, 12, 1, 16. So we multiply 19 times 10 is 190. 2 times 19 is 38. So we get 8, 2, 1, 228 for the carbon contribution, 28 for hydrogen, and 32 for oxygen. So if we add that, 8 plus 8 plus 2, so 16 plus 2, 18, carry the 1, 2 plus 2, 4 plus 1, 5, that's plus 3, that's 8, and then 2, so we get 288, so our answer is B. And again, keep in mind what we're doing here is just a review of Module 1 under the premise that ultimately, if we did not know the structure of testosterone and we were just given 288 grams per mole, could we find the molecular formula and then could we propose structures using data? How many degrees of unsaturation are present in testosterone? So we're given the structure. Let's just make a little table. How many pi bonds? We have 1 as a carbonyl, 2 as an alkene. So 2, how many rings? We have 1, 2, 3, 4. So that gets us 6 degrees of unsaturation. We could calculate it the other way as well. So the answer was C. So C19H28O2. We need to revise that. Oxygen doesn't affect the hydrogen count, so we end up with C19H28. For N equals 19, 2 times 19 plus 2 gets us what? 38 plus 2, that's 40. So C19H40. Again, that's the alkane molecular formula, fully saturated, minus C19H28. That's what we're given or what we found. We get H12. We divide by H2, so that gets us our 6 degrees of unsaturation, which we confirmed visually through counting pi bonds and rings. So what oxygen-containing functional groups are present in testosterone? So we have one here and then one here. So we have an OH group, so it's an alcohol. If this is the carbon bearing the alcohol, we see that it is bonded to 2 other carbons, and so that's going to make this a secondary alcohol. We see here a carbon-oxygen double bond. That's a carbonyl. What's bonded to the carbonyl? Carbon and carbon. And so that's going to make this a ketone. And so our correct answer for this will be A. And so now why is this important? Again, this will get to the second form of spectroscopy we learned called IR. And IR is basically going to tell us through that data there is an OH group and there is a carbon-oxygen double bond. So that's how we're going to confirm that, those 2 oxygens are there, and it's going to tell us, okay, it's present in an alcohol and it's present in a ketone. We'll be able to do that specifically. And so what is mass spectrometry? Again, abbreviated MS. It's basically molecular fingerprinting. And we went through the exercise of determining the molecular formula and then the molecular weight. But now what I want you to think about in terms of solving this problem is sort of working backwards. You're given the molecular weight, but then you have to determine the formula, and then ultimately, what is the structure? So you have this unknown substance, this powder, this liquid. You run it on this mass spectrometer instrument. It gives you 288, and then what do you do with that if you don't know what the structure is? So as this piece of data shows, this is a mass spectrum. The x-axis is m divided by z, where m is mass and z is charge. So what you're looking at in this data is actually ions. It's normally positive ions. And so for this, z is typically +1. So the numbers that you're reading on the x-axis are just, they reduce down to mass. So the y-axis is relative intensity, and that's another way of saying that is the abundance of each ion relative to the other. The first thing we want to look at in a mass spectrum is the signal with the highest mass. That's called the parent ion. So there's the plus charge. It's a positive ion. And the M is just the abbreviation of the parent. So the parent has all the elements and their ratio in the molecular formula. So you can see the number here is 288. And again, that's what we calculated from the stuff that we already know. So the parent ion, 288, is C19H28O2. And so what's a little bit more complicated in this right now is the presence of those oxygens. Can we come up with a method to determine, okay, yes, there's 1, 2, 3, 4 oxygens, or what if there's other heteroatoms? How do we figure that out? And so in the next couple slides, we'll go through that step by step. But the other important things in the mass spectrum, anything that's lower in mass is called a daughter ion, and those result from this thing called fragmentation. That's basically where the structure, for lack of a better way of saying it, falls apart, and it forms other structures. We can call them A, B, C, D, just to keep track. So they're lower mass ions, that still have some of that structure intact, but they're missing part of it. So those are called daughter ions, and they appear in these clusters or envelopes, and we'll talk about the pattern to those clusters, like why they have those patterns. But the other main signal we want to look at is called the base peak. And that's the peak that has 100% abundance. So if we draw a line over, we can see that the base peak is 100% abundance. So the base peak is at 100% abundance. Again, don't confuse that with the parent. The parent always has the highest mass. It doesn't necessarily have to be the base peak. Again, the base peak is the most common ion that results from the parent. So given a mass spectral data of M to Z equals 288 for testosterone, is there a way to calculate this formula, C19H28O2? Yes, there is. And the reason we can do that relies on the isotopic abundances of carbon, oxygen, and hydrogen. So if we circle back to general chemistry and just briefly review, what does the term isotope mean? An isotope of an element E, so this is your normal, H, C, O, N, F, whatever element. An isotope of element E has the same atomic number Z. So that's this number here. So again, atomic number, hydrogen's 1, carbon 6, oxygen 7, nitrogen, this should be C and O, nitrogen 7, oxygen 8, fluorine 9. So that's the Z number. But the mass number A differs due to a different number of neutrons. So if you've, just heard of any like sci-fi and they talk about isotopes, radioisotopes, you may have seen like carbon 14. And again, the 14 is referring to the mass change due to the different number of neutrons. And so it turns out naturally occurring elements can be present in these different isotopic forms. And so what are they? And this is just a brief table of the ones that will concern us for this course. So here's Z. Again, this is the atomic number. And we just get that from the periodic table. And so remember the superscripted number that occurs before the element, that's the mass of that element. So hydrogen has 3 isotopes. Hydrogen, 2H or D, or 3H or T. So D stands for deuterium, T stands for tritium, and tritium's a radioactive isotope. What's important as well is, you can see that mass increases. So this number 1, 2, 3, that's what you're seeing right here. Fortunately for us, as we'll see later on when we learn about NMR, proton or hydrogen is essentially 100% naturally occurring. We move up to atomic number 6, which is carbon. We see that there's also 3 isotopes, C12, C13, C14. The last one, C14, also being radioactive. And so that's what that propeller-looking symbol looks like, or means. Notice the mass, 12, 13, 14. Again, that corresponds to that A value. The an issue now that carbon is a little bit different. See, 98.93 is not quite 100. So there's about 1% of carbon that's C13. That will help us for mass spectrometry, for a way of calculating the total number of carbons. But it also really benefits us more for NMR, which again we'll learn a little bit later on. So nitrogen has two naturally occurring isotopes, N14 and 15, and nitrogen is essentially 100% abundant for N14. Oxygen has three naturally occurring isotopes, 16, 17, and 18. And so, as with nitrogen, oxygen is also pretty much 100% O16. The last four here are the halogens. Fluorine, we luck out. Fluorine is 19, it's 100% abundant. Now, chlorine and bromine both have two naturally occurring isotopes, chlorine 35 and chlorine 36. And what's important here is their ratios to one another, essentially 75-25 or 3-1. And so we want to pay particular attention to that. Chlorine is 3-1. So that's a useful tool for us. Bromine, atomic number 35, has bromine 79 and 81. Now look at these ratios. It's essentially 1-1. And so that's going to be a diagnostic tool for bromine. Iodine is 100% abundant, and it has the atomic mass of 127. So there are little clues in these isotopes that are going to help us when we look at a mass and the data to say, okay, this heteroatom is there or it's not there. So to restate the question, can we find the molecular formula just given the mass? And yes, we can. But before we get too far into that, I want to look at these other heteroatoms, nitrogen and the halogens, to exclude their presence, because they'll have diagnostic signatures in mass spec that can say, okay, it's there or it's not there. And so really the issue is oxygen itself, because it only has the oxygen 16. It's harder to diagnose just by mass spec. And really what we're going to have to do is once we learn IR will help us figure out if oxygen is present. But for now, we know it's in there. We're going to go through these other heteroatoms, look at their signatures, because they're really diagnostic, and that's going to help us develop this algorithm of saying, okay, what heteroatom is really in there. So nitrogen, chlorine, bromine, and iodine have signatures in the mass spec that if they're there, you can say confidently, okay, I know this heteroatom's in there. Then I further know it's going to have this mass contribution to the parent ion that has the molecular formula. Oxygen's a little bit more challenging, so we have to spend some time on that, developing the thought algorithm. So what other instrumental data can facilitate recognition of heteroatoms in a molecular formula? And again, that's going to be IR. Because IR is going to tell us specifically what functional groups are present. And most of them have oxygen, so that's going to give us a clue. Okay, there's an oxygen. If there is a nitrogen, the mass spec will tell us that. So the point of this is we must rely on these different techniques to tell us different things about the molecule. So this table summarizes the signatures, so the mass spec signatures that you'll observe in the parent if any of these heteroatoms are present. So if there is a nitrogen, because it's 100% abundant of N14, if there's an odd number of nitrogens, the parent mass must be odd. So if you're looking at a piece of data and the parent mass is like 47, so that's an odd number. You can say, okay, 14 of that 47 belongs to nitrogen. And then you make the assumption, okay, everything else is carbon and hydrogen. Now the flip side of this, if you have an even number of N, the mass is even. And so that is a little bit more challenging at that point. But again, we still have IR spectroscopy to rely on because we can figure out from our nitrogen-containing functional groups if there's things like an amine or an amide present. Fluorine 19 is 100% abundant. This one is kind of difficult to tell just because you're going to get an even mass when you include fluorine in a molecular formula. So fluorine's a little bit tough. Chlorine, you have two naturally occurring isotopes, 35 and 37. They're in a 3-to-1 ratio. And what that means is, again, your parent is your complete molecular formula. And so if you look 2 mass units greater than the parent, so M plus 2, if you see those signals in a 3-to-1 ratio, you can say, okay, that has a chlorine in it. And we'll look at visual examples of that in the next few slides. Bromine is 2 isotopes, 79 and 81. They're present in a 1-to-1 ratio. And so the same logic as with chlorine, if the M and the M plus 2 are equal now, then you can say, okay, there's bromine. In the diagnostic for iodine, which has a mass of 127, you might get lucky and see a signal at 127, or you can take the parent ion, subtract 127, and you'll see a daughter ion at that mass. So again, as we learn more about this, there's these different tests you can do on your data to say, okay, it has this or it does not have that. So let's go through these heteroatoms and visualize what I had just said on the prior slide. We're going to use derivatives of a compound called benzene. So this is benzene. It's C6H6. We're going to take one of the hydrogens, we'll call it X, and then we're going to substitute those different heteroatoms in and see how it affects the mass spec data. So the first one is called aminobenzene, commonly known as aniline. And so there's the amine group bonded to the benzene ring. And if you look at the highest mass here, So this number, it's kind of small, it's 93. So that's odd. Because it's odd, it's telling you that there's an odd number of nitrogens. The best assumption to make on your first pass through is, okay, there's one nitrogen. Then you take out 14 mass units from the 93, and then you run through that exercise we started the lecture with in determining the maximum number of carbons. Our next heteroatom is fluorine, and so this is fluorobenzene, so there's the halogen. This has an even mass, so it's 96. And again, that's going to be a little bit tough to really pinpoint that there's fluorine in there. However, when we start learning more about proton and carbon NMR data, we can look at signature signals in that data that will help us determine that fluorine could be present. So moving down the halogen group, we're at chlorine. So chlorobenzene. If we scan over to the highest mass, we see a parent mass of 112. And then we keep reading over, we see there's another parent peak at 114. Now, if you draw a line from the top of those over to the abundance, we could say, okay, that reaches 100% abundance. Now, if we do the same thing for the peak at 114, that's hitting right about 35%. Abundance. And so the ratio of those is 3:1. And so really it's you're looking at the heights of those two peaks relative to one another. It's a visual thing, so it's 3:1. That's telling you there's chlorine in there. This signal is due to the chlorine 35 isotope. And then this signal is due to the chlorine 37 isotope because they're present in a 3:1 ratio. The next heteroatom is bromine, so bromobenzene. We have the bromine attached to the ring. Now, if you scan over to the parent region, you see the parent mass at 156, and then you see the M+2, the parent +2, at 158. And you can tell just by looking at those ratios, they're in 1:1. Now keep in mind, if you're to draw the line over to the abundance axis, they're hitting, somewhere 65 to 70% abundance. But relative to each other, they're 1:1. The most abundant peak is at 77. And remember, that has a different name. That's called the base peak. So with chlorine and bromine, it's a visual thing of looking at the parent. With iodine, so iodobenzene, we scan over, we see that iodobenzene has a parent of 204, but we also see a signal at 127, and that is diagnostic of an iodine atom or iodine ion being present in the mass spectrum. Alternatively, if we take 204 and we subtract 127, what we'll find is we get this peak at 77. So this is the 204 is the total molecular formula. 127 is the iodine ion. And then we get this fragment here, this daughter ion at 77. So really this plus that equaling the molecular formula confirms that iodine is present in the molecule. And so that's not as bad as fluorine. Iodine can be a little bit tricky in figuring out, but again, other pieces of data can help us confirm it. So based on the abundances M to M plus 2, which of the following contains a bromine atom? So I've normalized these abundances of the parent, and then this is the parent plus 2 mass units. So if there's bromine, we're looking for a 1-to-1 ratio. And as we scan down, we can see that C matches that 1-to-1 ratio the best. Given those ratios, which would contain a chlorine, so chlorine has to have a 3-to-1 of M to M plus 2. So they're the same ratios as before, so we can eliminate C. We see that A is the correct answer. We have a 3-to-1 ratio. And again, for chlorine, that's the chlorine 35 isotope, and the M plus 2 is chlorine 37. Given the following values, which contains a nitrogen atom. So we're looking for an odd mass. 64 is even, 45 is odd, 62 is even, 44 is even. So our answer is B. And so just to visualize, explain a little bit more about the process here. So let's write H, C, N, O, atomic masses. H equals 1, C equals 12, N equals 14, O equals 16. So how can we convert a mass of 45 into a molecular formula? Because it's odd, we're going to say, okay, there's 1 nitrogen. So this is all atoms of the different elements. We can say, okay, 14 of that is due to nitrogen. So we get 31. Then we're going to assume, okay, the remaining 31 must have C plus H. Then we follow what we started the lecture with. 31 divided by 12. So we know just by looking at it, it can't be 3 because 12 times 3 is 36. So this number is going to limit us to 2 carbons. So 12 times 2 gets us 24. That's the carbon contribution. So we can now say 31, which is our C plus H, can have a maximum contribution from carbon being 24. And so we subtract that, and so this has to be 7. So the molecular formula is C2H7N. And now, does this make sense with what we know in terms of finding degrees of unsaturation? So N subtracts from the hydrogen count. So we have 1 nitrogen. So our C2H7N has to become C2H6. Using the alkane formula, CnH2n plus 2, C2 must have 6 hydrogens. So we found a molecular formula of C2H6. So we get H0. So this has 0 degrees of unsaturation. So overall, yes, C2H7N is a reasonable molecular formula. And then we could go even further. C2H7N. It's basically telling us we must have all sigma bonds. So we can't have any pi bonds. We can't have any rings. There's no degrees of unsaturation. So we could say, okay, here's 2 carbons. Now I need to bond it to a nitrogen. And then I end up with 3 hydrogens plus 2 plus 2, that's 7. So that would be a reasonable claim. This would be a primary amine. We could also draw one more constitutional isomer. This would be a secondary amine. So just from that single piece of data there, 45, we're able to work through all this, find a molecular formula, and draw some structures. So what about a parent with an even mass? So right away we know there's no odd number of nitrogens. There could be an even number, but the question then stipulates we're told there's 1 oxygen. What's the maximum number of carbon atoms that can be present? And so pay attention to this wording. So maximum does not necessarily have to equal the right answer. Again, because we're just bracketing, what's the maximum number of carbons we have? We run through the exercise, does it make sense? If not, we knock that end down 1 digit. So let's run through this. M to Z equals 46. So that's C plus H plus O based on what we're told. 12, 1, 16 atomic masses. We're told there's 1 oxygen. So we get 30. Remaining C plus H. So 30 divided by 12, again, that's going to get us 2. So the answer is B. 12 times 2 is 24. So how do we figure out the H count? That's the carbon contribution. So 30 minus 24, that gets us 6. That's the H count. So the molecular formula, C2H7 2H6O. We saw from the prior problem that for 2 carbons we need 6 hydrogens. Oxygen doesn't affect the hydrogen count, so this also has 0 degrees of unsaturation. And we can draw 2 constitutional isomers, so this would be a primary alcohol, or we could stick the oxygen in the middle, that would be an ether. And so both of those obey the molecular formula. There's no degrees of unsaturation. Furthermore, we could do the uniqueness. 2 unique carbons, 3 unique types of hydrogens in a ratio of 3 to 2 to 1. The ether has 1 unique type of carbon, 1 unique type of hydrogen in a ratio of 6. So those differentiate those constitutional isomers. And so that's going to wrap up the introduction lecture to Module 2. It's kind of a long screencast, but it's pretty important for us in understanding the logic of taking the actual data that we're given, converting that mass spec number into a molecular formula using the isotopic abundances, using degrees of unsaturation, proposing structures, and then as we learn more about IR and NMR, and we're given data sets, we can actually zero in on one specific constitutional isomer.